Have you ever witnessed an engineering paradox that defies everything you thought you knew about aviation? The Airbus A380 embodies exactly that. An aircraft that climbs slower than planes half its size, yet represents the pinnacle of aerospace achievement. Wings that bend like palm trees in a hurricane, yet carry 560 tons across oceans. But what makes this giant truly extraordinary aren't the specifications you can find on the internet. It's the revolutionary engineering solutions that shouldn't work, but do. Problems that stumped Boeing's best minds, solved by thinking backwards. All while maintaining commercial viability in an industry where 1% efficiency determines survival. Today, we're revealing the 10 most incredible engineering achievements of the A380. From deliberate performance limitations that save millions to materials that didn't exist when the project began. And I guarantee, whether you're a pilot or passenger, you'll discover something that transforms how you understand this magnificent anomaly. In 1988, Airbus engineers gathered in Hamburg with an impossible assignment. Create an aircraft that moves 800 people efficiently between megahubs, fits existing airports, and somehow makes money. The conventional wisdom said, pick two, you can't have all three. What followed was a 17-year journey that would consume $25 billion, require inventing new sciences, and nearly destroy Airbus twice. The program, initially coded A3XX to maintain secrecy, would demand solutions to problems that didn't have names yet. The result? 251 aircrafts that prove sometimes the impossible just takes longer. Here's something that baffles every pilot transitioning to the A380. 4 engines producing 280,000 pounds of thrust. Yet the aircraft climbs like it's embarrassed to leave the ground, 1,500 feet per minute, when a 737 manages 3,000. This isn't failure, it's genius. The slow climb solves 3 critical problems simultaneously. First, wake turbulence. When 560 tons displaces air, it creates horizontal tornadoes with 250 miles per hour rotation speeds. A steep climb concentrates these vortices into invisible killing zones that persist for 5 minutes. The shallow climb disperses them, preventing smaller aircrafts from being flipped like toys. Secondly, fuel optimization. Those massive Trent 900 engines have an efficiency sweet spot at 85% thrust. Push beyond that for aggressive climbing, and fuel consumption increases exponentially. The gentle climb keeps all 4 engines in their optimal performance band, saving 2,000 pounds of fuel in just the first 10 minutes. Third, the structural preservation. During ascent, the wings transition from supporting wheel-borne weight to carrying everything. That transfer creates enormous stress. By climbing gradually, peak stress reduces by 30%, extending the wing's lifespan by years. Singapore Airlines calculated that the slow climb saves them $4 million annually per aircraft. What looks like weakness is actually economics made visible. The A380's wings don't just generate lift, they shapeshift continuously throughout flight. Watch from a window seat, and you'll witness something remarkable. Wings that flex up to 13 feet during normal flight. But that's just what you can see. Hidden inside are 20 fuel tanks that transfer kerosene between them automatically, changing the wing's weight distribution and flex characteristics in real time. As the wings bend upward, fuel pumps outboard to counter the flex. Too much turbulence? Fuel moves inboard to dampen oscillations. But here's the breakthrough. The wings use adaptive camber technology. Microscopic adjustments to leading and trailing edge positions change the wing's shape hundreds of times per second. Like a bird optimizing its wings for different flight phases, the A380 continuously morphs its aerodynamic profile. This system revealed something unexpected during testing. The constantly adapting wings were 4% more efficient than rigid wings in real-world conditions. Chaos, it turns out, is more efficient than perfection. At 43,000 feet, outside air pressure is lethal. Your blood would boil in 15 seconds. Yet inside the A380, passengers experience pressure equivalent to just 5,000 feet elevation, compared to 8,000 feet in most aircrafts. This wasn't just about comfort, it was about biology. At 5,000 feet, your body absorbs 40% more oxygen than at 8,000 feet. Passengers arrive measurably less fatigued, with lower stress hormones and better cognitive function. The engineering challenge was immense. Lower cabin altitude means higher pressure differential. The fuselage fights 9.4 psi, trying to explode it every second. Airbus developed a radical solution: variable thickness skin panels, chemically milled to be thicker at stress points, thinner elsewhere. The result? Strength without weight penalty. But maintaining pressure in a space larger than 3 tennis courts required reimagining air systems entirely. The A380 uses quadruple redundant pressure controllers that can maintain cabin altitude even with 2 massive holes in the fuselage. During certification, Airbus proved this by deliberately blowing 2 square-foot holes in a test fuselage. The pressure remained stable. The noise level between an A380 and 777 is immensely different. The A380 measures 56 decibels in cruise, technically 4 times quieter than other wide bodies. This wasn't an accident, it was obsession. Airbus employed 40 acoustic engineers whose only job was hunting and killing noise sources. They discovered sound, traveled through unexpected paths. Hydraulic lines transmitted engine vibration. Air gaps around doors created whistle frequencies. Even passenger reading lights generated measurable cabin noise. The solutions bordered on fanatical. Hydraulic lines got vibration-damping sleeves. Door seals used triple redundant inflatable barriers. The engines mount on pylons specifically tuned to cancel certain frequencies through destructive interference. But the masterstroke was the cabin air system. Traditional aircrafts blast high-velocity air through small vents, creating whoosh. The A380 moves larger air masses at slower speeds through oversized vents. Same cooling, 70% less noise. The silence has unexpected benefits. Passengers sleep 23% longer on A380s, according to Lufthansa studies. Crew fatigue reduces measurably. Some airlines report fewer passenger complaints simply because the quiet environment reduces stress. Building the A380 required reimagining manufacturing itself. Components built in 4 countries had to unite with millimeter precision. The logistics challenge made D-Day look simple. Consider just the wings. Built in Wales, they're too large for any cargo aircraft. Airbus created a purpose-built ship, the Ville de Bordeaux, just to transport A380 components. From Bordeaux, specialized barges navigate rivers. Then, convoys with motorcycle outriders travel on routes surveyed for overhead clearance, requiring removed street signs and trimmed trees. The final assembly facility in Toulouse is larger than 50 football fields. It had to be, because unlike traditional assembly where the aircraft moves, the A380 stays stationary, while armies of workers and robots swarm around it. 7 separate assembly stations work simultaneously on different aircrafts. The coordination requires military precision. A single delayed component cascades through the entire supply chain. In 2006, mismatched wiring harnesses, German sections 3 centimeters too short for French fuselages, cost Airbus $6 billion and delayed the program 2 years. Yet when it works, it's magic. Every 4 days, a completed A380 rolls out, assembled from 4 million parts sourced from 1,500 companies across 30 countries. Every A380 flies with an invisible twin, a digital doppelganger that experiences everything the real aircraft does, but faster. When turbulence strikes over the Pacific, the digital twin in Toulouse feels it instantly and ages the aircraft years in minutes of computation. This predictive modeling goes beyond simple monitoring. The system learns each aircraft's personality. Manufacturing tolerances, repair history, and route patterns create unique digital fingerprints. The system can identify specific aircrafts by vibration patterns alone. The payoff is prophetic maintenance. Components get replaced weeks before they'd fail. Problems get fixed before pilots notice them. The result? 99.7% dispatch reliability, meaning A380s almost never have mechanical delays despite being flying cities of complexity. Emirates engineers discovered their digital twins were predicting issues so accurately that they reduced spare parts inventory by 30%, saving millions in carrying costs. Stopping 560 tons from 170 miles per hour, landing speed requires serious engineering. The A380's carbon brakes can absorb 121 megajoules, enough energy to power a house for a week. But the innovation isn't the power, it's the intelligence. The brake-to-vacate system is automotive adaptive cruise control reversed. Tell it which runway exit you want during approach, and it calculates perfect deceleration to reach that exact point at taxi speed. Too much braking wastes energy and wears components. Too little blocks the runway. The system considers everything: runway surface, slope, wind, weight, temperature, even brake heat from previous landings. During certification, Airbus demonstrated 100 consecutive landings where the aircraft stopped within 3 meters of target. That's like parallel parking a building. This precision matters at congested airports. The A380 can consistently exit runways 1,500 feet sooner than manual braking allows, freeing runways minutes faster. The A380 contains 10 tons of titanium, but not where you'd expect. It's in the floor beams separating the two decks. This wasn't the plan. The plan was aluminum. Then physics intervened. Supporting 300 upper deck passengers requires incredible strength. Aluminum beams would intrude into lower deck headroom. Carbon fiber couldn't handle point loads. Steel was impossibly heavy. Titanium was the only solution, despite costing 15 times more than aluminum. But titanium is notoriously difficult to work. It destroys cutting tools, requires argon atmosphere welding, and work hardens unpredictably. Airbus developed entirely new manufacturing techniques: electron beam welding in vacuum chambers, cryogenic machining that freezes titanium during cutting, chemical milling that dissolves material atom by atom. The result? Floor beams 40% lighter than aluminum alternatives while supporting 50% more load. Passengers above have no idea they're standing on more titanium than exists in most fighter jets. Managing 320,000 liters of fuel across 13 tanks while maintaining perfect balance requires computational orchestration. The A380's fuel system doesn't just store kerosene, it conducts a symphony. As fuel burns, the aircraft's center of gravity shifts, but it must stay within an 18-inch window on an aircraft 240 feet long. The system transfers fuel between tanks continuously, maintaining balance while optimizing for efficiency. The system is so sophisticated, it anticipates needs. Climbing? Fuel moves forward before the nose rises. Descending? Fuel transfers aft, preemptively. This predictive balancing improves fuel efficiency by 2% simply through optimal weight distribution. During testing, Airbus discovered something unexpected. Random passenger movement actually helped. The fuel system's responses to minor imbalances created a dynamic equilibrium more efficient than static perfection. The A380 doesn't fly alone. Every aircraft connects to a global network sharing operational data in real time. When one A380 encounters severe turbulence, every other A380 approaching that location receives warning within seconds. This collective intelligence extends beyond weather. Engine performance patterns, system anomalies, and maintenance discoveries propagate across the fleet instantly. A solution discovered by Qantas Maintenance in Sydney updates Emirates procedures in Dubai within hours. The network revealed surprising patterns. A380's flying certain routes developed specific wear patterns. Engines on Middle East routes degraded differently than Pacific routes due to sand particle ingestion. The system now predicts maintenance needs based on route history, not just flight hours. This shared consciousness has achieved something remarkable. The global A380 fleet operates with higher reliability than any single airline could achieve alone.